pair will be retained in the product. But the relative stereochemistry of the two pairs with respect to each other, it can be different. Let me illustrate this in the molecular model, in which I slightly altered now. This is the same setup that we had before. The dienophile comes in, concerted reaction approaches. Okay? Now I've labeled with blue the diene to be trans-trans-diene. These two guys point to the same regional space. In the cyclohexene, they will wind up cis to each other. This one I've labeled red. Stereochemistry is retained. When it adds, in the cyclohexene that's formed, these two red guys will be cis to each other. But will all four of them be cis? Will one pair be cis to the other pair, or will the first pair be trans to the other pair? And the difference between those two is how it approaches. It can either approach this way, or it can approach this way. Okay? And that gives you a different orientation of this pair relative to that. Already in the approach, you can see clearly there's a big difference between these two. Okay? And that will show up in the product. And so I show you this on the slide. On the two dimension of the slide, here is the trans-trans hexadiene. And we've got this dicyanoethylene. It can approach in this way, where the two substituents, the two nitriles, point to the backbone of the diene, point to these two carbons in the back. That's called endo. There's the alternative, where the two nitrile groups point away, more or less into outer space, if you want to call it that, away from the back of the diene. Okay? And it turns out that endo is preferred, the so-called endo rule. And the reason is complex. A lot of textbooks say it's because of what, hand-waving of what's called secondary orbital interactions, where the orbitals of the, particularly with conjugating electron withdrawing groups, resonance electron withdrawing groups, overlap with the back carbons, okay, of the diene. Okay, so if you have the red coming in this way, notice that the red is closer to the backbone of the diene, and that is favorable. But there are other reasons. There are many factors that come in here. So we won't discuss that because that's beyond the scope of this course. But we'll just take the endo rule as the preferred mode of attack. Counterintuitive, actually, so this is a classic case of kinetic control because the endo attack gives the endo product, which is actually sterically slightly more hindered, and therefore thermodynamically the less stable compound. In this case, the reaction is so exothermic, remember it's at least around 40 kcals, that there is no equilibration as we did for the hydrobromination of butadiene, where we discussed kinetic versus thermodynamic control. And that only worked because the kinetic product could revert at slightly elevated temperatures to the alkyl intermediate and eventually the thermodynamic product form. Here, to get the Diels-Alder product to undergo what's called a reverse Diels-Alder or retro Diels-Alder reaction, you have to really blast it to 200 degrees or higher, typically done in the gas phase, and not always synthetically advantageous. So you can't get out, you don't equilibrate. You get the kinetic product, and it's rock stable. So these are the two approaches, exo and endo. So I'm doing it here once over, but now for cyclopentadiene. Cyclopentadiene, remember, it's forced to adopt the S-cis configuration, and so it's rather reactive. It's stereochemically labeled by necessity. The two double bonds are cis, and the substituents or substituent that gives it the cis-cis stereochemistry is actually the one carbon that links, that closes the loop, the ring. Right? You can think of this carbon as a substituent to this bond, there's a cis substituent, and a substituent to that bond, there's again a cis substituent. Okay? So it's stereochemically labeled. And I'm feeding it this diester, and you can approach it two possible ways. The ester groups point away, that is exo, that will be the exo addition, and when you're all done, notice that in the cyclo addition, the two substituents on the represented by this carbon on the inside of the diene, they move up. And these two substituents move into the same position in space as the bridge. So they're all cis. This bridge is cis to the two ester groups. In the endo, which is the favorite mode of attack, the bridge moves up, but the two substituents wind up down. Okay? Also often said the endo groups. So we can show a little movie on that. So here's cyclopentadiene. Here is the endo approach and the endo attack. And so here it comes in, and notice as that the bridge, what becomes the bridge, this substituent group, this methylene group, starts moving up as these two carbons hybridize. And these guys all move down as these two carbons hybridize, also indicated here. The esters are a little messy here, a little large, but the action part is here. These two carbons of the dienophile and these two carbons of the diene. And then it's rearranged so that it looks the normal way. So here's what the way we would picture this approach. And in the endo approach, in this case, the inside substituents, meaning this group here, of the original diene, wind up trans, or anti, to the substituents on the dienophile. So here's another example, now no longer cyclic. Back to the trans-trans-pentadiene and the dicyano system, shown again. As this approaches in the endo transition state, these nitrile groups point to the backbone of the diene. When you're finished, all of these groups wind up cis to each other. Okay? This is now really confusing, right? So, and you really need to have good stereochemical view to be able to digest that. And on a piece of paper, it's really quite murder, actually only achievable after a bottle of scotch. Yes?
So is the endo rule just preferred, or is the only thing that happens?
It's the only thing that happens.
And what happens if, like, you have, say, cyanide on one side and some, like, other functional group on the other side of your dienophile? Which one is the endo side?
What do you think?
Bigger one?
You get a mixture.
Oh, you get a mixture?
Yeah, unless there's some, like one of them is just absolutely huge, and so if they're both equally activating, more or less, then you would push the larger group to the outside. So you would get some selectivity. Okay. That's the next level up. That's good, okay? You guys are good at coming up with questions that are totally unanswerable. So, since I don't want you to all become alcoholics, I'm giving you a very simple mnemonic device that is really very, very simple. You just label the substituents on the diene as being outside or inside. So we got two outsides, this and this, and this one is the inside, O and I, right? And then the electron withdrawing group on the dienophile I label A. So in the end, the endo result is that the O's and the A's wind up cis to each other. As simple as that. You don't have to go through stereo acrobatics in your brain and get lost in trying to see things in 3 dimensions. But I think you should confirm that with a molecular model, and you can see it, or with one of these examples. And so you can see here the 2 metals are O, right, and the cyanides are I, and they all wind up cis to each other. The way I've drawn it here, they all point down. If you were to come in from the top, they would all point up. That would be the corresponding mirror image. So yes, so I can do this also. That's why I did the model. Here's the endo transition state. It comes in like this. And see, that's why it's not totally obvious in 3 dimensions. As you make a carbon-carbon bond here and here, that is the product. Okay, so notice what happens. These 2 hydrogens back off. They stay up on top. These 2, the red ones, point down. These guys move up too, meaning that this one moves initially into the axial position, and these 2 become equatorial. And that means that even though you sort of envisage them to go up like this, in the final ring, they wind up cis to the corresponding red. Okay, so all of them are cis in the endo transition state. Okay, so we call it dienophile. Dienophile means dine, loving, comes from philos, Greek, to love, loving. I had 6 years of Greek at high school and 9 years of Latin in high school, and I'm sure none of you know what I'm talking about, but that's where it comes from. But of course, it takes 2 to tango, so the dine also loves the dienophile. Okay? And so the movie that I'm showing you now shows you the love dance of dine and dienophile, so to speak, where the dine says, "Bring it on home to me." There you go. B-line. Whoa. Unbridled molecular copulation. We don't do that nomenclature, so forget it. So no stereochemistry except for the dime. So now we're going to do stereochemistry. Endo rule. Starting with exo. So here's cyclopentadiene, and there's a CN triple bond, acrylonitrile. Exo approach. See how bridge and this wind up cis. The bridge is inside, I. In the exo transition state. And wedges and dashes, you can see, that's cis to that. Now endo. And here's the supposed secondary interaction. Plausible. Works for some systems. But the point is that substituent and bridge are trans. Because the bridge is I, and this guy is the A, and so they're trans to each other. Wedge, that. So practice that. But using that mnemonic device, actually, you have foolproof outcome in your stereochemistry. Now, the Diels-Alder reaction is quite general for a whole bunch of double bonds and dines, including triple bonds. And triple bonds, actually, you may recall from chapter 13, have higher energy content than double bond, and often that translates into higher reactivity. Similar thing happens at Diels-Alder reaction. They can undergo Diels-Alder cycloaddition. The rules still hold. You want to have an electron-poor triple bond. Okay? It's much simpler than a normal dienophile because the triple bond turns into a double bond, no stereochemistry, except, of course, the concertedness means that these 2 substituents will wind up cis to each other. But they have to anyway because you're making a 6-membered cyclohexene. And so here in this case, 4 plus 2 cycloaddition makes a cyclohexadiene, a wonderful molecule, full of functionality to be elaborated further. There is an interesting twist here, namely, this is a dienophile, and now we're making another double bond that could potentially also function as a competing dienophile because this is also an electron-poor double bond. But it does, but it's much slower than this guy for 2 reasons. One is the triple bond is more reactive in general. Secondly, it's more hindered. Okay? So indeed, if you use one equivalent of this, one equivalent of that, it will stop here. There's no competition. However, if you use excess butadiene, or in a separate step, take this guy and add more butadiene, it will undergo a second Diels-Alder reaction. Okay? And that, when you're done, makes this. So you can do this all in one pot. Excess butadiene, 2.5 equivalents or more, plus that, bang, out comes this in very high yield. That is an incredible transformation. Okay? You're getting a glimpse of what's to come in later chapters. Some introduction of molecular complexity in a very, very simple transformation. 4 new carbon-carbon bonds have been made. You get a bicyclic system. 2 double bonds are still there to do stuff, and the whole thing occurs completely stereospecifically out of necessity because the Diels-Alder reaction is concerted. Okay. So the second class of reactions that fits in here is the class of electrocyclic reactions. And here we are dealing with communication of the 2 ends of a diene or a trine or a tetraene, such that they start moving to overlap the 2 end carbons to make a carbon-carbon bond, and at the same time rehybridize the terminal carbons to become sp3, a ring closure. And that has it's a very simple reaction. It's an isomerization. Nothing is added, nothing comes off. Just simply the ring closure, and you move the triple bonds around to satisfy the picture. So let's do this for 4-membered and 6-membered rings. So when you take cyclobutene and you heat it up, activation energy is about 33 kcals, translating into about 180 degrees in the lab. Still acceptable. A little bit at the high end of what organic chemists like, but it's still acceptable. When you go much over 200, all hell breaks loose, and synthetic chemists don't like that. But that's fine. This thing will ring open to make butadiene. So this is the reverse of the electrocyclic closure. It's reversible. Okay? This reaction from left to right is actually exothermic, and that's an exception in the case of electrocyclic reactions because of ring strain. All the others, the ring closure of the open acyclic polyene to the closed form is exothermic, as we'll see in the hexatrine to to cyclohexadiene closure. So in this case, because of ring strain, the reaction is exothermic to the right by about 10 kcal. So it's an equilibrium, but it's way on the right. Now, what's beautiful about these electrocyclic reactions, you can do them thermally, where they are controlled by thermodynamics, the heats of formation of the components, so straightforward thermodynamics. You can also affect them by light. And with light, thermodynamics is out the picture, if you wish. You overcome it because you're exciting the molecule with a photon to a very high-lying excited state, and then it falls down into any one of the sides of the equilibrium. Does that sound familiar? Yes. Our entire planet is a kinetic scenario driven by the sun, the sunlight. It's the sunlight that makes it possible that all of life, or nature, vegetables, humans, exist. Because in an oxygen atmosphere, none of us should be here. We should spontaneously combust, because we're all incredibly unstable with respect to carbon dioxide and water. And it's not just us, even more maybe clearer is gasoline, right? There you have a hydrocarbon, totally combustible, that's how we use it, but it's stable. It's kinetically stable because fortunately, oxygen, while reactive, is not so reactive that it will chew us up and make us disintegrate in the oxygen atmosphere. So light can drive this reaction too, and light can drive it uphill, as it's often called, from a thermodynamic standpoint. And you can control whether you go from left to right or right to left by the choice of your wavelength of light, which can be easily done with a laser. Okay? This is one of the rare cases where we will do photochemistry in a very rudimentary fashion. Basically, you just put h times nu up here, and I won't even ask you to pick the wavelength of the light. I will give you the fact that you will pick the right wavelength so that left goes to right or right goes to left. Okay? So with light, you can do it either way. With heat, the cyclobutene will always ring open in an exothermic manner. So here's some marvelous movies from based on quantum mechanical calculations. So these are actual pictures from my colleague Stefan Immel at the University of Darmstadt. And so here's the ring opening of cyclobutene, and going back and forth. So when it closes, notice this is sp2 hybridized. It will have to become sp3 hybridized. And notice very clearly there has to be a rotation. So as the ring opening, it has to rotate to disentangle these two guys. So that's to make a bond between the orbitals and rehybridize. Now let's look at cyclohexadiene as the last thing today. And it does the same thing, but now the ring opening is endothermic, or to put it differently, the ring closure is exothermic. Okay? So hexatriene on heating, it has to be cis, right, because the two ends have to find each other. On warming, activation energy a little less actually than cyclobutene, so you can go a little lower in temperature, will nicely close to cyclohexadiene. And you can indicate that again by doing your arrow pushing. And the reason this is now exothermic from right to left is because there's no ring strain in cyclohexadiene, or very little ring strain in cyclohexadiene. And again, you can drive this by light from left to right or right to left, based on the light you choose. And the light you choose, of course, this is based on what you will understand that. You did UV spectroscopy, UV visible. It's the chromophore. Then you have a UV spectrum. You shine light into one of the peaks of the that is exhibited by either one of these compounds selectively. And so it basically photo bleaches the system because it'll go away to here, where, if you go from left to right, where this guy doesn't have a band. And so it's not affected by the light if you pick the wavelength properly. And conversely, going from right to left will do the same thing. So now the big question that we'll answer next week is, what is the stereochemistry of that reaction? Very similar question we just answered for the Aldana. Thank you and have a nice weekend.